So open and closed loop feedback system, one of the topics. So basically, um, what we have discussed in our class is basically uh, a part of a control system like the transducer, actuators, logic controller. So there are the components that make up a control system. So in control system, basically we want to achieve a desired level of our input. So a typical control system consists of subsystem, which we will look into more details. Yeah. So this subsystem is put together for the purpose of um, controlling and also manipulating the output of the process. So in modern control, uh, the practice in the modern control engineering include the use of control design strategy for improving manipulation process, and also we aim to improve the efficiency of the energy. Okay, and there are many other things that we want to control. So a control system allow us to basically handle huge equipment or process with low error, and also on top of that the system run autonomously or automatically with minimum supervision, and also the system can be basically operated remotely and able to work under very minimum influence on error or disturbances. So in general, there are two types, okay, of control system. The first one is the open loop and closed loop control system. We will look into that. So since the advent of industrial revolution 3.0 basically, so that's mark the uh, main the important progress of control system, or basically industrial control system, where the use of controller uh, based on op amps to provide control function. So since then, this field has grown into much more complicated and much more efficient system, okay, especially with the use of machine learning, okay, smart algorithm. So nowadays, okay, the industry have moved or shift into industrial 4.0, where basically on the basis, okay, of the technology advance is control system. So we look into this simple and classical control system. So this is a classic control system, and also we will say a simple control with a simple control mechanism. Uh, So we need, when we discuss about a control system, we need to understand, okay, the parameter that we want to uh, control, and also what are the um, basically the variables, okay, other variables that involve, okay, in the control system, okay. So if we look into, okay, this water level float regulator, okay, it's a simple mechanism where it use a float, okay, uh, to regulate the water level inside, we can call this as a plant, okay. So basically, this, okay, plant or this vessel, okay, receive water input, okay, and the water goes into the vessel, and the level of the um, water is controlled by the amount of water flow, okay, water flow that comes into the vessel, okay. So the float is basically attached to a link, or that open and close the valve that allow the water flow. So basically, you can see, okay, there are a few components there, okay, involved, and so basically there's a fire or heat, okay, boiling up the uh, water, and turn the water, when the temperature rises, is turn the water into steam, and let the water vapor to go out. So so the water basically evaporate, okay, into steam with the use of heat, okay. So this system start with a subsystem called input transducer, which converts the form of the input that used by the controller. Okay, so we need to okay, identify, okay, what are the uh, transducer, okay. So basically, we need to know what are the transducer, and then we need to know what are the controller, and we need to know what are the input parameter, or basically the desired parameter, okay, and then what are the manipulate variables, okay, manipulated variables, Okay. Next, we need to know what is the main plant. Main plant. And what are the disturbance? Okay. So what are the disturbance that uh, basically influence the desired parameter? Okay, and one last thing is the actual, okay, uh, parameter or the output, right? Okay, so this is a, a simple closed loop control system where, okay, basically the input or the desired parameter is basically the water level. Okay, the water level. And so how do we measure the water level? Okay, by, okay, the based on the float. So basically the float is the transducer. Okay, float is basically the transducer, okay, that basically measure the height, okay, estimate the actual height of the water level, okay. And so and the flow or the water flow, okay, is controlled by the opening of the valve, okay, which the controller receive the input, okay, from the float. So this is valve is our controller, okay, and the manipulated variable is basically the water flow, and okay, the main plant is the vessel, and the disturbance, okay, is basically the steam or water vapor that uh, comes out from the system, and the actual, okay, parameter is the actual height that we desire lah, basically. And this even is steam due to the heat lah. Okay, so it when water evaporate, so it reduce, okay, the level of water. Okay, so perhaps if we like to draw, okay, the system, so we have our input, okay, the, let's say H, the input, okay, uh, the desired input, okay, and then the transducer, okay, basically float, okay, that converts, okay, uh, the water level, okay, and create an error signal that input into our controller, which is the valve, okay, valve. And the valve, okay, basically control, okay, uh, the output of the valve is basically the water flow, flow. And this is the vessel lah. Okay, the vessel. And there's a disturbance here. Okay, negative steam. Okay, basically this disturbance due to the water turns into steam, and we get the actual output. Okay, we can this is HI, this is HA, and okay, the actual output okay is measured by the float. Okay, so that's a simple control system, closed loop control system, where we have identified the control element, the manipulated variables, the main plan, the disturbance, okay, the actual outputs, the transducer, okay, okay, and then the actual input and actual output. Okay, so this is another example, classic mechanism, watt flyball governor. Basically, a centrifugal governor is a specific type of governor with a feedback system that controls the speed of an engine by regulating the amount of fuel uh, admitted into the engine. Okay, so basically the main objective is to maintain a near constant speed irrespective to the load or fuel supply condition. So it's basically uses the principle of proportional control. It was invented in 1788 by James Watt to control his steam engine, where it regulates the admission of steam into the cylinder, okay, or to the engine. So it regulates the amount of steam coming into the engine by manipulating the opening of the valve. Okay. Its widest use was on steam engine during the steam age in the 19th century. It is also found on internal combustion engines and variously fuel turbine and in some modern striking clocks. Okay, so basically you can see the mechanism. There's a fly ball where the spinning fly ball will regulate okay the amount of basically amount of fuel that comes into the engine or into the chamber. Okay, so this is a simple manual control system. Uh, Manual control system for regulating level of fluid. Again, we have another example of level fluid control in a tank by adjusting the output valve. Okay, but this manual control, this is a closed system, but it is manual. Whereas the human is operate as the do two things. Okay, first measure the level of water or level of water inside the tank, and also control okay the amount or the opening of a valve. Okay, so the transducer and also the controller is basically the human operator himself. Okay, for this example, okay, if we again in this example we want to regulate the level of liquid, okay, h, okay, the height or level of liquid. What this use is visual sight. Okay, look into the small window to estimate the amount of water height. So if the water reach, okay, the maximum limit, so the operator will open the valve and let, okay, the water fluid to go out. Okay, so the control uh, variable is, okay, basically the water tank height. The manipulated variable is the fluid input, okay, and basically the output. Okay, so control variable is this is fluid input. Seems that we have no control, or uh, the human here have no control on the fluid input. Okay, uh, they only have a control of the fluid output for in the vessel. So it seems like that. Okay, because this fluid control coming from the other system. So basically, okay. So the edge, if we try to, okay, draw the edge input, or the basically the height, the desired height, okay, and then compare with the measured height. So this is the transducer visual, uh, uh, or the eyes of the operators, and compare, okay, the uh, and then you have the error. And so basically this is the the controller. So the human, okay, the human uh, and send the signal to the actuator. The actuator is basically uh, the uh, hand, okay, the hand, and the output is the fluid output. But the input from fluid input, okay, plus from the fluid input, okay, fluid, and here is this fluid output, and you have the plant, okay, basically the tank, okay, the tank, and we have, okay, the actual output or height, water height, water level, okay, and then observed by the visual eyes of the human eyes. So this is a simple manual control system by regulating the water fluid. This one, the steering or the control system of now car navigation. Okay, so basically, we have a desired travel. Okay, uh, and the driver, okay, is the controller. Okay, and then the actuator is the plant mechanism, and the plant is the automobile. The output is the actual cost, and the actual cost, okay, there are measurement, uh, uh, for example, the speed of the car, okay, and all the visual from the human side, okay, and also the vibration, okay, also becomes um, the sensor lah. Basically, this is the sensor. Okay, like for example, if the car, okay, has skidded to the left or to the right, like for example to the left, so the driver can sense the too much vibration. That means the car need to be pulled back to the main road. Okay, and then the output is the uh, actual, okay, the uh, yeah, the actual cost travel. Okay, they compare to, okay, becomes the error, or the difference between the desired and the actual cost of travel. So yeah, so the error signal basically is the control level action by the driver. So a modern control system. Okay, so there are few important subsystems. So we have basically looked into the few examples before. So the uh, subsystem, the important are the control device, okay, the actuator, the process itself, okay, and then uh, we have the input, okay, but to compare the input desire and then the measured output, okay, the measured output, okay, to compare we need a sensor to convert, okay, the actual output into measured output, okay, like this one. So we have the actual output, so we need to measure output. So the comparison here, okay, must be in the same unit or the same quantity lah before the control device, okay, can make any correction. Uh, so a control device, okay, is often the controller that replace the human in the conventional control system. Okay, so an open loop control system doesn't compare, okay, or the output with the input. So an open control system utilizes a control or control actuator to obtain the desired response. So it doesn't actually care, okay, for an open loop system. What is the resultant output with the given input? But a closed loop control system have feedbacks to compare the actual output to the desired output response, okay, for any given input or reference. Like we have really close to us our air conditioning system. Okay, so we can basically, it is a closed loop system where when we press the remote control temperature level, So basically, we are setting the input or reference. Okay. So the system, our AC system has a temperature sensor. Okay, and the temperature sensor will measure the uh, actual output or actual temperature of the room. Okay, and then compare with our input or reference. So the basically the controller, okay, will determine whether there any error value or error input. So if there is there any uh, error error value, so basically the controller, okay, will turn on the plant. Okay, in this case, it will turn on the indoor unit compressor of the AC system. So the indoor unit and compressor basically will operate, okay, until the desired input or reference is achieved, or until the error, okay, the error difference, okay, between the input or the reference and the measured output is equivalent to zero. So this is what I have explained. Okay, what happening into our room temperature control. Okay, so this is another example. Okay, in the industry. Uh, so the input or the set point, okay, is basically set by the operator, and the the PV signal is feedback. Okay, set PV. Let me go. Okay, SP is the set point. Okay. Uh, anyway, the difference between the set point and the PV, I think is the measured value, the measured output. Okay, basically it's the PV. Uh, so the error signal is sent to the controller, and based the program algorithm, the controller will make decision and send the output to the industrial electronic or the actuator lah. Okay, so the actuator may consist of amplifier, relays, okay, and also a three-phase current controller that supply the energy to the heating system. So, the heating, okay, will cause the uh, output temperature, and the output temperature will be measured by a temperature sensor compared to the set point that we want to measure. This is another control system, the thickness control, uh, to control the thickness of a paper coming out in a paper mill. Okay, so whereas the thickness of the paper, okay, can be determined or adjust, okay, depending on the quality, the desired quality. So the desired or the set point of this control system is to control the thickness of the paper. So there are several sets of important parameter here and then system that we need to know. Okay. For example, we need to know what is the input parameter and then the output parameter and how is the output parameter is measured. Okay, and what is the controller. Okay, and then what is the actuator in the system, and also what is the plant. Okay, so the input signal is the set point, the thickness. Set point is the thickness. Yeah, let's say the thickness h set point. Okay, and the set point is compared to a sensor. So in this case, the sensor is based on LVDT. The never LVDT. I think we have discussed about this LVDT or the linear variable device transformer. Okay, basically measure the displacement. Okay, a small displacement based on inductive principle. Okay, it can sense small displacement. In this case, displacement is measured to relate the thickness of the paper coming out, okay, from the plant. Okay, and so the sensor is so basically a signal converter, like convert the input or the output of the LVDT into the same value, okay, that can measured by the digital controller basically. Okay, okay, and then the digital controller is the controller, and then the digital controller, okay, sends this is digital system. Okay, digital system, so it works at digital level. Sends so need to digital converter, digital to analog converter lah basically. Change the digital output, okay, into an analog, and then the analog, okay, control the in this case the actuator is the worm screw motor, which adjusts, okay, the roller, okay, position. So the roller is basically the plant, okay, that compress the wet fiber coming out from the plant. Okay, so if we were to uh, draw, okay, so we have a set point. Okay, or desired input. We compare with the measured output. Measured output is measured by the LVDT. Set point is the thickness measured. And this is our output thickness. Okay, and this is our measured output. Compare with the set point. Okay, set point. So we have our error. So error, okay, is measured by the digital controller. Okay, our digital controller here, DC, and then the digital controller will give input. Okay, but before go to the input to our actuator here, so it needs a DAC, and go to our actuator. This is the motor, and then our plant. Here is our plant. So our plant is basically movable roller. So our plant adjust the distance between the movable roller, and then adjust the thickness of the paper. Okay, the edge it can be edge in the input, and then the edge out. Okay, the output thickness. Right. So things the similar thing we can see here. Okay. Okay, where in this system, where we want to control the water level. Okay, H, the water level, and the water level is measured by a capacitive probe, and then the capacitive probe sends the signal into a controller, and the controller basically sends output signal or controls signal to a control valve. Okay, and then this basically valve works on air pressure. Okay, air pressure. So the controller control the valve and then open the actuator is the motor lah, basically motor. Okay.
Doctor,
Yes.
I have a question from previous slide.
Yeah.
Okay, for the warm screw key motor, right?
Yeah.
Then that one will adjust according to our set point.
Yes.
Or so the based on the thickness, the warm screw motor will adjust the roller.
Yes. Yes. Correct.
So yeah, so the LVDT will be the transducer to measure the thickness.
Yes.
Mm.
Yeah. So LVDT is just measuring the output. Okay, the output, the outcome, the actual outcome. But the worm screw the position will be determined by our set point. Okay, not the LVDT. LVDT is a measurement device. Okay, where it measure the thickness, and then convert into measured output. Okay, so same unit lah, same level or same quantity that can be processed by the digital controller.
So this one open loop or closed loop?
This one is a closed loop. Closed loop. Okay,
Okay.
closed
Okay.
loop as shown in the below. This is a closed loop.
Okay.
So this is also a closed loop. Another example, similar to the earliest example that we have seen. Okay, before. So basically, we want to manipulate or we want to control the water level, and we have some manipulate variable, which is the water supply, water supply or the water flow, and the water controlled by the valve. Okay, manipulated by the motor. Okay, but they this not based on motor. This is based on air pressure. Air pressure, it's not more air pressure. So I think this is another valve, yeah. Modeling control valve. Not based on entirely motor, or basically I think there's a small uh, uh, motor, yeah, that control the pressure coming into this valve. This is a valve control device. Okay, and then open the water supply. So it is similar. Uh, if you compare with the first, or I think the first example, okay, uh, we have seen before. So this water outflow, okay, in this example seems not uh, controlled by the controller. So we assume that this water outflow, okay, is just open. Okay, so this is become the okay, disturbance lah. The disturbance, okay, water outflow. So let's try.
Doctor,
Yes,
I have a question.
yeah,
If let's
yes.
say the closed loop system, I want to convert to open loop system and just remove the LVDT for the previous slide.
Okay, if you remove the LVDT, yeah, correct.
Yeah, it's become open loop.
Open loop, there is no comparison between the set point and then the measure output.
Mm,
So the drawback is that um, so you may have no control. You may have no control of the output.
mm,
Okay, it's like trial and error. Okay,
okay.
okay, you try and error. But if you have a closed loop system, uh, s- so the system can make the decision for you.
Okay.
Okay,
Okay.
let's try. Okay, so we have our set point. Okay, and this is water level. Uh, Set point, the water level, and then compare. So the measured uh, output, compare with the water level, is provided by the capacitance probe. So this is basically the transducer. It convert physical variable into electrical signal. Okay. So the set point, okay, maybe like then compare with the measure output. Okay, and then come to the controller. Okay, and then the controller. Okay, so this is the error. The controller here sends the electrical, so the error. So this electrical signal, okay, electric signal to a valve. Okay, and the valve, okay, give air pressure, and then okay, the plant, which is the tank. Uh, uh, the thing is not about this relay. Okay, relay. Okay, open the pressure. Go to the valve. Okay, and then the valve, okay, air, water supply. And then go to the tank. So, and then we have this, our disturbance, the water outflow. I think would here. Sorry, not there. Okay, this is the water outflow. Okay, so coming out from the valve is the water supply. I think the missing part is the relay, and go to the tank. And the actual water level measured by the capacitance probe. Okay, so this is the disturbance lah, basically. Okay, that's how we identify the subsystems in water level control. So this is like a much complex system with multiple input and multiple output. Okay, like for example, the multiple input here is the water, fuel, and air. And okay, whereas the level of the water, fuel, air is set into the computer. Okay, and then the computer uh, manipulate the actuator or the valve that um, uh, gets into the boiler. Okay, and then the boiler go to the turbine, and then the sensors that measure, okay, the output to produce to the measured output, and they compare into the computer. So this is one multiple input control system, or multiple input, multiple output control system. Okay, or the process variable PV. Okay, PV is the process variable or the measure output. So this a typical control system block diagram with the input reference or set point, compare with the process variable or the measure output, producing the error. And the error, okay, is go into a controller. Okay, and it can be here we have P, I, and D, and then the controller will determine, okay, the process the output the error into the manipulated variable of the plant, and then we have the output. Okay, okay, or the okay. So this example is we have a PID. PID, okay, basically stands for proportional, reset, or integrate, or rate or derivative. Okay, where the PID controller has a specific purpose into a control system. Okay, like for example, to uh, to control or manipulate the final output gain. So you use the proportional, or you want to control the or to reduce the transient time or time response. Okay, like the overshoot or the uh, rise time of your, or okay, rise time of your uh, output response. So then we use the integrate or derivative. So I'm not going to go into details lah. So those are the typical controller used in the industry lah, still relevant. And also we basically have looked into the programmable logic controllers. Okay, in the how it is used, like the PLC, okay, relay switches. Okay, we have seen in the first chapter, okay, early chapter, PLC, one of the computer to solve the logic used for in controlling industrial devices, still relevant until today. I think that we have done this example before, and also have seen the example